going to talk about the transportable array. You've heard a lot about the transportable array in the lower 48, and my job now is to talk a little bit about the transportable array plans in Alaska and Yukon. So I'll spend only a few minutes introducing the transportable array. I think everybody here sort of knows the basic operation. I'll try to describe our deployment plans for Alaska and Yukon, the geography, where we're actually going to deploy stations, the schedule of when we'll put the stations out, and some of our approaches to handling the logistics of taking the stations out. And just to make it challenging, I'm going to interleave actually a different talk about one of the station design aspects, which is related to emplacing broadband sensors in areas of permafrost and tundra regions, and trying to improve the performance of these stations, specifically the long period horizontals. This is a subject that has some parallels in OBS deployments in shallow water, for example, or even in deep water where you get a lot of tilt on the horizontals, and also in portable deployments. So we've been trying to do some testing to figure out what's the best way to get really good data. And the aspects of this affect both the permitting. We have to explain to the land managers how we actually are going to construct a station, and it affects the logistics and also the budget of the plan. So I'll try to whiz through this as quick as I can. So this is the canonical map of the transportable array, its current location. On the right-hand side is a picture of some of the vaults that we use. We move about 200 of these stations every year. We've been doing that now for about 1,600 sites. We have an annual budget of about $9 million. So in this current design, we utilize this underground tank. This tank is about 1 meter across and buried about 2.5 meters deep. You can see in the pink area in the shaded map in the center, we've been doing this rotomolded tank in the center part of the U.S. and eastward for quite a while. That was a design improvement to help make the stations more reliable and to yield better data. But we recognize that that particular method may not work in Alaska. It's one of many things we'll probably have to change as we go to Alaska. So we've been measuring the performance of the transportable array. We have a formal metric that we have to report to the National Science Foundation about our data return. But I'm going to concentrate mostly on the station performance in terms of its seismic noise performance as seen on the ground, not the sensors self-noise or anything, but actually what you can get when you install the sensors. And in the lower left, you'll see a picture of what we call a power spectral density, and shows a stack of 6 years worth of transportable array data from vertical channels, all stacked together. So there's some 27,000 spectra all stacked on this plot. And I'll explain a little bit more about those. What we do is take an hour-long time series and just stack these up and form a little sort of topographic map of how high the spectra will stack up for a certain amplitude at a certain frequency. This is all available at the DMC. They have tools that any data that goes to the DMC, they do these calculations on it, and you can see the plots on it and compare how your station does relative to other stations. This is following the McNamara and Boas method. So one of the things that we do is we take some specific frequencies. In this talk, I'll focus mainly on this long period, that's 100-second band, and see how the horizontals do at different types of stations. What we do as well is we form little timelines of these different frequencies, and you can show a shift in the long period performance where it gets suddenly better. This is very helpful in comparing what types of techniques actually work well. The other thing that we can do is form a histogram of these stations. Is how well did they perform at these frequencies. So here's a little histogram. The green line again is the long period vertical performance. Shows that the TA stations for this time period, 2006 to 2010, are sharply peaked That is, they all perform about the same, quite good performance, minus 178 dB at 100 seconds. On the horizontals, it's not quite as good. The horizontals are noisier by about 30 dB, and they're more broadly distributed. That is, some stations perform better, some stations perform worse. What we'd like to do in Alaska is try to improve this by shifting the long period performance of the horizontals at 100 seconds. It basically scales at 30 seconds to even longer periods, but 100 seconds is kind of an indicator of how well you're doing. We'd like to shift this over by 20 dB or so to minus 165 or so. So this is the plan for Alaska. The idea is to put about 300 sites out in a grid-like spacing. What's shown here in the light blue dots are the proposed grid spacing. And what's shown in the dark blue dots are the existing seismic stations that are already real-time telemetered to the IRIS-DMC. So you can see there's lots of seismic stations already in Alaska, many of those distributed along the Aleutians and in the subduction area. So not all of these are broadband seismometers, so we've gone through a process, and that was the last slide that Max showed, which was comparing the existing broadband stations and the existing PBO stations for which ones match up with our dots, so we can decide to utilize the existing infrastructure if it's there. But you'll notice that there are many regions in Alaska or Canada which have no stations, and so we'll be concentrating most of our deployments in those areas. Each station will have a broadband seismometer, infrasound, pressure. Some will have these meteorological sensor packages, which have wind speed, wind direction, outside temperature, outside barometric pressure. We expect them to be all to have communications. Most of them will have real-time communications, but some of those may burst their data in let's say 4-hour windows or maybe once a day. But at least at the end of the day, we're expecting to have the data back from all the stations. There's a sort of phased deployment, which I'll get to in a little bit, but the general spacing of this grid is 85 kilometers. It's slightly bigger than the 70-kilometer spacing that was done in the lower 48. And I would just want to emphasize that the grid looks nice, but there's, as people have pointed out, lots of earthquakes. This is 1 year's worth of earthquakes in Alaska, and there's lots of topography. So we have to work around quite a few complexities in Alaska. So our basic idea for the station design is to have a sensor emplacement scheme that will achieve the highest quality data, particularly in the longer periods and on the horizontals. We'd like to have a power strategy that will balance the weight and reliability against the complexity of too many types of systems that are turning on, turning off. And this will likely center around basically the same idea that PBO uses, which is solar panels charging big banks of batteries. We tend to favor, at this point, a more advanced chemistry battery, so not as many batteries, not as heavy a batteries, but still about the same number of ampere hours, essentially 18, the equivalent of 18 car batteries inside of a box. The communications, that will be a variety of different communication schemes. There's limited cell phone coverage, but there is some VSAT, there is some existing internet service, there are some DSL or phone line service that you can connect to. So that'll be a mixture. And we will also likely use a service provided by Inmarsat, which is a BGAN machine-to-machine communication system that we have a firm quote on providing that service at a couple hundred stations. So here's the idea for the sensor emplacement. It involves trying to put this long period seismic sensor down a deep hole. In certain cases where we have a rock outcrop, we might core a hole with a conventional sort of concrete cutter diamond drill coring machine. These can core an 8-inch diameter or 6-inch diameter hole down about 1.5 meters or almost 2 meters in about an hour. We've done this at 4 or 5 places now. Once at Albuquerque Seismic Lab, that's where this picture is taken from. But we've also done it in the Yukon and in Anza. So this is a little picture of the guy running the stand with the electric-powered coring drill going down into the rock here. In other regions, which are more frozen soils and gravels, which we expect in many parts of Alaska where there's no outcrops, we would use a kind of portable augering system to helicopter that in and land and auger a hole and put in a casing. So this gives a kind of picture of the station. You'll recognize this hut. It's a fiberglass hut, weighs about 500 pounds or so. It has solar panels mounted on it. There's a 3-component broadband sensor that is down this casing here. Is a PVC casing that goes down about 5 meters. Inside of the hut is a data logger and local data storage and the power systems and so on. So this is one style that we would use in sort of soil type environment. This picture is actually taken from the University of Alaska's Toolik Lake Field Station. If you've been there, it's all along the Dalton Highway, about 120 miles south of Dead Horse, north of the Arctic Circle. And so there's a PVC cased hole, goes down 5 meters there. Or, like I said, in rock outcrops, we would do a 1 to 2 meter coring into the rock. So that's the basic strategy. We're looking into a slightly more simple design instead of this hut to eliminate some of the weight of the batteries by using these lithium iron phosphate batteries for increased energy density, which we can fit inside of a box that's like 1 meter wide by 25 inches or so by about 24 inches tall. That's what looks like one of these boxes. This is actually a picture of a PBO station, but it's a similar idea, a box mounted on an aluminum frame with solar panel frame sticking up. So there's some economics here when you compare how much it costs to actually fly around a lot of batteries, even though these higher energy density batteries cost more. When you factor in the cost of helicoptering a bunch of batteries around, we think that we'll save some money by a smaller package that's easier to transport. So this is the basic concept for the operations. We would establish an operations base in Anchorage. It happens to be around the corner from the PBO office in a similar kind of office warehouse complex. We would have some hubs at little villages throughout Alaska, or places where you can commercially ship freight into these locations, or at least stage a sort of logistical operation out of there. And then you would helicopter out to each one of these remote dots, maybe 7 to 20 of these dots around any particular hub. So the hub would be a sort of logistical operation that might span anywhere from 12 days to 30 days of operations out of that particular node, and then we would move on to the next node. That's the basic idea. Here's our deployment schedule. So we're here in 2013. This is 2014, where we would be removing some of the stations at 200 per month or 200 per year in the lower 48, and then 2014 we would install 26 stations in Alaska, then 44 the next year, 64, 94, and then 42 in the last year, building up to about 300 stations over the course of these 4 years. So this is a fairly slow ramp up. It still is ambitious undertaking, trying to install 80 stations in one summer. It's going to be difficult. We'll actually work probably from late spring all the way through early fall, not try to jam everything into the summer. There are many areas in which working in the shoulder seasons where the ground is frozen is actually preferable to working when it's a couple feet deep in water. So we'll take advantage of the different areas that we can work in different times of the year, just like we do now. So this gives you an idea of the map again. We have this shown in red some of the test stations, and these purple squares indicate areas where we're going to start to recon for this summer, a group around existing stations, and then some more stations up here. So I'm just going to quickly go through some results just to emphasize that we think this augering stations into a borehole works well. It's worth the cost. So this compares our station at Toolik Lake. It's been there since 2011 against the Kola GSN station in Fairbanks. This is a 100-meter deep borehole into solid rock. And here's the verticals against the horizontals. So if you don't know how to read these power spectral densities, then you can look forward to some other part of the talk, I guess. This is a comparison, actually, of one of Doug Christensen's sites, a sort of portable Pascal type of experiment, where, again, here we have a vertical on the left, horizontal on the right. This is at Toolik compared to the Toolik station that we operate now. So you can see there's 20 or 30 dB difference in the horizontal noise. This is a comparison of the stations that we operate at Toolik Lake, or sorry, POKR Flat, where in this case we compared on the bottom, this is vertical northeast of a TA tank, just like the ones we use in the lower 48, against a 5-meter deep borehole. And you can see that the borehole is pretty comparable, actually better than the TA tank. And this is a comparison of an experiment that the Pascal guys, Tim Parker, went there and just buried a broadband sensor within a meter of the surface and using a hand auger and stuck it in there. It does really well in the winter, especially. This is just the north channel across the top. So here's the 1-meter hole. This is the TA tank, and then this is the 5-meter hole. So it's a little more noisy. And then it got worse as the ground temperature warmed up and the sensor is more exposed to pressure-induced tilts. So this one is much less susceptible to that type of noise. And then this is a picture just of the one that we did at on the Dempster Highway at Eagle Plains. It's a cored hole, 8 inches, about 55 inches deep into the rock. Again, you see this hut sitting here. So this station has been operating all winter, and the seismometer going into the hole. We have a little stop-action video of the install, but it went pretty well. Here's just a comparison of the standard AEIC type of or steep type of deployment, where you dig a overpack drum in about 1 meter and pour some concrete in the bottom and stick the trillium into the bottom of the tank. You see that the horizontals are very noisy. This is similar to mini Pascal experiments or flexible array deployments. We went to the same place and augured in a 5-meter hole into this loess. It's not very competent soil even. But the seismometer does much, much better, minus 47 dB improvement on the horizontals, 20 dB improvement on the verticals at 100 seconds. So you get pretty good improvement even in a not-so-great site using this method. So here's just a summary of the performance improvement. We can get this performance target of minus 168 or so dB from these kind of deployment methods. We think this is a reliable way to install sensors in this region that'll yield good quality data. So that's my conclusion. Thank you.